Wasabi, you guys, Silver here, and I'm about to show you, in my opinion, the 10 most unfair integrals from MIT Integration B. There are a lot of integrals from MIT Integration B that I think is just kind of a little unfair, because some are like you're required to have like math Olympiad knowledge. Not only that, some is like you have to know some outside math courses to solve this, and some is kind of like real analysis rather than undergraduate calculus. So let's go ahead and start with our first integral that I think is very unfair, and that is this nasty integral from MIT Integration B 2006. I don't know if this is a regular round integral or a semi-final, but I know for sure that this was not in finals round. Or maybe this was final. No, I don't think it was finals round. But this integral in general is hideous. Okay, if you put this in Wolfram Alpha, well, the first time when I put this in, it said that there was no standard integral function. But I think Wolfram Alpha updated. But this integral is hideous. Okay, the way I solved this integral is I actually did use trig substitution, and then I used semi-integration by parts, and that's how I solved this integral. For me, at least, the human way. But apparently, the actual solution to this integral, it uses like reverse quotient rule. Apparently, this integral is reverse quotient rule, and what you do is you turn that 2 into 1 plus 1, and then it cancels out into like, you get e to the x of some, what? You get like 1 over this denominator plus square root of 1 minus x squared over 1 minus x? Something like that? Or something close to that. I don't know. I don't remember. But it was nasty. Apparently this is a reverse product rule, or reverse quotient rule. And that was the answer. And this, I think that was just kind of nasty and BS. It is horrid. It is god horrid. Even if you do trig substitution, it is horrid. It is god awful. For number 2, it is this integral. All of you have already seen me made a video of this, and I'm just disgusted. I'm still disgusted that this integral existed, and they put this in an Integration B competition. I would never do something like this, because this is just bad. To whoever who had this integral, like, I feel so sorry for you, because this is just god awful. It's literally 2 reverse product rules. That's literally the solution to this integral. It's 2 reverse product. It's a double reverse product rule. I don't remember how, but you do some trig manipulation with this for some identity, and then you get whatever the answer. I don't know, but it was nasty. All right. Again, this is just kind of unfair. Horrid, horrible, horrible. Number 3 is this integral. You've also have seen me attempted this integral as well. This is from 2022. They classify this as a regular round, I believe. I think this was a regular round integral. Yeah, I don't know why, but this is also nasty. Okay, I cannot believe this is also another one of those reverse quotient rules that they do. It's like they ran out of ideas, and they're just like, oh, let's just come up with a random reverse quotient rule and just put it in. And this is what they came up with. That's just awful. That's god. First of all, that's cruelty, and I feel like, well, the way I would make reverse quotient rule integrals is it just has to look pretty much like G main, but a little nicer. But this is even worse than G main. Okay, this is just awful. All right, number 4. The way I solve it is I use periodicity, but it is difficult. It's a very challenging periodicity integral, and if you've seen Integration B training for that section, I did solve this using periodicity, and it was god horrible. But why am I putting this here? This is actually an unfair integral, and the reason is because when you go against opponents, if you're using periodicity, you can have an opponent that could solve this in like 30 seconds. And you're probably asking, how on earth can someone solve this in less than 30 seconds? So apparently, the quick solution to this is to use linear algebra. And I'm just like, excuse me, what? Yeah, apparently you use orthogonality to solve this integral quickly. I don't know what that means. I mean, I know that orthogonal is like 90 degrees something. I don't know. I'm not a fan of linear algebra. I only know like basic linear algebra. I don't remember or have the knowledge of advanced linear algebra topics or something. I don't know. But apparently, to solve this very quickly, you use orthogonality or some linear algebra topic. But yeah, if that was the case, that's just unfair, because can you imagine like you're all prepared for just only knowing calculus tricks, and then all of a sudden they pull a linear algebra on you, and then this linear algebra student, oh, it's this answer because of some linear algebra theorem or whatever. That is just unfair. It would make sense if it was like a basic linear algebra topic, but I highly doubt, well, maybe it's just me. I tried looking at solutions for this integral, and not a single one of them talks about orthogonality. So if you know what they're talking about when they said like solve this using linear algebra, please make a video or tell me, because I kind of want to know. But from what I searched up about orthogonality, I see no relations. Number 5. What the hell is this? Okay, honestly, I don't even know what this means. Let's be real. Okay, a piecewise function is already nasty enough. If you know me very well, I hate these. I hate piecewise functions. And now I have to deal with this? Why? Who made this? Well, actually, I do know who made this. And I despise them. But why? Why would you do such a thing? And the fact that the answer is literally this? Well, what I mean is like, the answer is literally 10 times 10 to the power of 10 over 10 factorial. Like, what? What? Like, to anyone who does not know what this is, like, I'm so sorry for you. Number 6. This is a quarterfinals round integral, and this is from 2022. I'm gonna be honest. This was pretty cool. This was legit pretty cool. But the reason why I clarify this as unfair is because not that many people knows how to speed integrate with piecewise functions. Like, there's rarely any resources that teaches you, like, they probably know how to integrate with these type of functions, but do you know how to speed integrate with these functions? A lot of the majority of the people, no, they don't, because it's not that popular. So to anyone who does know how to speed integrate with this, it's like, it's a little unfair, because for those who doesn't know how to speed integrate this and they see this firsthand, like they sight read this integral, they're kind of forced to just graph or to constructively sum it up. But the thing is, this is not easy to constructively sum, because this is a double summation. Okay, when you speed integrate this is not just a sum, it's a double sum. This is literally a double summation. So to graph this or to constructively sum this is just a little unfair for those people who does not know how to speed integrate with piecewise functions. Don't get me wrong, this is a very cool integral. This is probably one of the most unique integrals, probably one of the most beautiful integration bee problems. But I honestly think that this was also unfair for the competitors. Not only the double summation was unfair, we have this 7th integral, a semi-finals round. What were they thinking? Why would you put this in semi-finals round? Why? I wouldn't even put this in an integration bee at all. So for those who don't know, this is a Glasser's math. No, actually, I lied. This is not Glasser's math theorem. This is a Glasser's master corollary. Okay, it's one of those sub branches within Glasser's master theorem. But then there's like a corollary and a corollary, and this was one of them. And they put this in semifinals round. Let's be real, not that many people knows the Glasser's master theorem. I think nowadays they do now because, I mean, after 2-3 years ago, it got popular now. Despite all of those Glasser's master videos on YouTube, or the MIT Integration B walkthrough YouTube videos, okay? Glasser's master theorem is still not that popular, okay? To throw a corollary of it is just rude. Like, this is just straight up rude. And now it's like, for those who don't know Glasser's master theorem, they can still solve this, but how? They use freaking Lebowski measure, whatever. I don't know how you pronounce that name, I don't know. But it's you use one of those, it's pretty much a real analysis topic. And they solved it using that with this. And if you're just some undergraduate calculus student and you're thrown with this in Integration B, you're pretty much a goner, because there's no way in hell to solve this without using the Glasser's master corollary or some advanced real analysis knowledge. Like, this is just god awful. God. And it's even worse the fact that it's more rude the fact that they put this in semifinals round. Number 8 is this one, the finals round integral. Okay. So you can solve this integral. There actually is a very nice solution to this. Thank Chronos Decay who revealed the actual solution to this. I think it was really cool. But again, despite that it was an easy solution, I highly doubt anyone would come up with it, because I don't think I've seen anyone who used this, the original solution. The other YouTube videos I've seen with this, people use like trig manipulation or complexifying the integral, and it was nasty. It was nasty. Let's be real. Okay, a 20-minute video on this. Okay, thanks for the explanation. But how would you actually solve this in less than 3 minutes? Because I highly doubt that sight reading this and then using trig manipulation is gonna make you solve this in less than 3 minutes. I highly doubt that. Okay, I highly doubt a G aspirant would solve this in less than 3 minutes. Okay, don't even argue with me. No. Without the knowledge of complex analysis, you cannot solve this in less than 3 minutes. Okay, let me actually show you the trick to this and why I think this is unfair. When I say complexifying this integral specifically, I'm not talking about this. Okay, obviously, like turning everything in terms of i's, like what it was, like 20ix plus 3 21i. No, like we're not doing that. Okay, we know that's nasty. We know that's nasty. Algebraically, that's nasty. Okay, but we're actually using modulus, meaning we are using z. We're not using z like e to the ix. No, we're using modulus of z, and this is talking about the square root of a squared plus b squared. In other words, this is equal, well, we're using like what a stands for, like, or pretty much like cosine or sine here. But I mean, we rarely use that because, I mean, let's face it, right? This is equal to 1. I don't know why I put plus 1. Equal to 1. Pretty much the integral that we have, I think it's this, actually. Now I think about it. I think it was actually this. And then, yeah, I think this looks right. This seems to be the right solution. Yeah, because you get the trig functions and the other trig function here. I think this seems to be the correct solution. And then I mean, because it's absolute value, you get to pull out the 20z. But you pretty much, you simplify and it becomes something nicer. Something like that. But yeah, that's the solution. Not exactly. I did something wrong. I don't remember. But it was something in that sort of concept where you use modulus. I'm very sorry to whoever had to deal with this. This is just ugly. If you don't know much about your complex analysis stuff, or if you're not very good with your complex algebra, you know, I'm so sorry for you. Number 9. This integral, also nasty to use trig manipulation. But did you know that someone also told me that you can solve this in less than a minute? And I'm just like, how? You know what they responded to me? Representation theory. And I'm just like, what the hell? I'm sorry. Are you talking about abstract algebra representation theory? And they were just like, maybe. I don't know. Someone has to be trolling with me. But at the same time, I don't know my fields or like those abstract field or whatever, because I'm not into that type of pure math. But apparently, someone told me that you use representation theory to solve this very fast. And I'm just like, huh? Excuse me? What? And again, not a single video or a solution that I've seen uses representation theory. To anyone who does know how to use representation theory to solve this, please make a video or explain, because I don't get it. This whole nastiness being squared and you're telling me representation theory? What? No, I don't believe it. But if that is true, that's just cruel. This is evil. Very unfair. Number 10 from MIT Integration Bee 2023. I think this was a regular round. I don't know. It was regular round or quarterfinal. I think this was regular round. But oh my god. For those who don't know, this function is from a Math Olympiad problem. If you have no Math Olympiad knowledge, I'm sorry. If to anyone who has sight readed this integral, like I am very sorry if you have no Math Olympiad knowledge. It's kind of favoritism towards Math Olympiads. That's why I don't get me wrong, I like MIT Integration Bee problems up until like 2022. And that's where it's just like, okay, this is just getting out of hand ridiculous. But that's just me. But I'm sorry, but I kind of think this is kind of favoriting Math Olympiads. Yeah, in order to solve this, it's a factoring problem, pretty much. There's a way to factor this, and then it cancels out the square root, and then you end up with like two radical integrals where you use like nasty trig sub or hyperbolic sub. So not only you have to pass the Olympiad barrier, but you have to speed bash your way out. And again, you only have like, what, 2 minutes to solve this integral? It's nasty. It is literally nasty. Okay. I'm going to put this in as a bonus. This is a tiebreaker integral. And yeah, what the hell? This is so unfair. If you know nothing about real analysis, or even if you do have real analysis knowledge, if your real analysis skills is not competitive or advanced enough, good luck solving this. But I mean, at the same time, I have seen people who hasn't taken real analysis, and they kind of still understand the concept of this. Like, you have to have a very good in-depth knowledge of how improper integrals work. Like, I mean, like, theory. Okay, not just computational wise. I would not be able to solve this. But apparently I was told that this telescopes. And so, because there are if you simplify it enough, and you get like an f of x plus 1 minus f of x. Real analysis wise, it telescopes. And so it equals to 0, but you get like a leftover term, which equals to 1/2. And that's why the answer to this integral is 1/2, because of that leftover term. Yeah, this is unfair. To anyone who has like horrible real analysis knowledge. Yeah, integration B should be for calculus people. Like, come on. Or at least give us like like a syllabus of like what topics is gonna be expected in this integration bee. But no, apparently it's a wild card, and we get this bullshit. SMH MIT. So yeah, that's about it. That's all the 10 or 11, I guess, most unfair integrals from MIT integration bee, in my opinion. Let me know which integrals you think is the most unfair integral that you've seen in MIT integration bee, or maybe in some other any integration bees. Definitely share them with me in the comments. Alright, thank you so much for watching, and I'll see you guys in the next video.